Hi, everybody. Welcome back to the Feynman technique. Today, I'd like to find a general formula for any integral in this form. Sometimes this is referred to as the um, a reciprocal Gaussian formula. But anyway, this form shows up a lot, so I'd like to develop a generalized formula for it. Okay, so let's see. We already have a parameterized integral. So let's just start doing Feynman integration on this right away. Let's evaluate this at the point b is equal to 0, and let's see what we get. If we evaluate this at b is equal to 0, this term vanishes, and we're just left with this, which is a standard Gaussian form, and it is equal to 1/2 the square root of um, pi over a. Okay, now let's take a derivative with respect to b. So I prime of b is equal to the derivative with respect to b of our original integral. Now the Leibniz rule for differentiation under the integral sign says that we can bring this directly inside the integral. All right, and now let's evaluate our partial derivative right here. Well, this is going to be equal to, we're going to get this part back, and then times the derivative with respect to b of this, which is just going to give us over x squared, and it's going to be a negative. So now I prime of b is equal to this. And it looks like we made things worse. But with a clever substitution, we can relate I of b to I prime of b. And the substitution we're going to make is this. We're going to let x equal the square root of b over a times 1 over u, implying that dx is equal to the square root of b over a times negative 1 over u squared du. All right. And also, it means that x squared is going to equal, let's see, that's going to be equal to b over a u squared. All right, let's plug in our substitution here. All right, so all our x squareds just become b over a u squared. All right, so all our x squareds become that. Our dx becomes this. And our bounds of integration, let's see. This is going to change to 0, and this is going to change to infinity. And we are done with our substitution. So let's go ahead and clean this up. Let's see. Take care of some negative signs. This negative sign, we'll use it to switch the bounds. And we'll leave this negative sign out there. See, this is a constant, so it can come outside. Let's see. This 1 over u squared will cancel this 1 over u squared. All right, this is going to come outside our integral as an a over b. All righty. And let's see, you can divide the top and the bottom by b here to get 1 and 1, and then just bring this to the top. And let's see, this a cancels this a, and then let's go ahead and put this as the leading term. All right. Let's see, this will come inside our fraction as an a squared over b squared. And now we can do some canceling. That a cancels this a, this b cancels this b, and we just have the square root of a over b times this. And now you'll notice this integral right here is exactly our I of b. It just has a different dummy variable. But that was the purpose for the substitution. All right, and now this is equal to negative square root of a over b times I of b. So now we have a differential equation. Let's get rid of this middleman right here. All right, so now we have this. And what we can do is divide both sides by I of b. All right, now we can integrate both sides db with respect to b. So let's put an integral sign there, and then let's bring out the square root of a, and we'll make this a b to the negative 1 half. Okay. So let's see. This we can evaluate with the substitution u is equal to I of b. Therefore, du is equal to I prime of b db. And then we have the form 1 over u. So this, the left-hand side evaluates to natural log of I of b. And that's equal to negative square root of a times, let's see, b to the 1 half over 1 half, which is just 2. And then we have plus c. All right. Now we take both sides as an exponent on e. We raise both sides. Well, we take both sides as an exponent on e. So for the left-hand side, we're just going to get I of b. And for the right-hand side, we're going to get c times e to the negative 2 square root of ab. All right, so there's our I of b. Now we need to solve for our constant of integration c. Well, we know this. We know that I of 0 is equal to 1 half the square root of pi over a. But that's also equal to this when we let b equal 0. If we let b equal 0, this whole exponential term right here cancels to 1. So we just have c is equal to 1 half the square root of pi over a. So our I of b finally is just equal to this. And let's verify that. Let's go up here and grab our integral. And let's paste in some values for a and b. We have 1 and 1, and let's make sure that it's actually equal to this thing. All right, so for the case where a is equal to 1 and b is equal to 1, these things match up nicely. Let's see if we just drag this a along. Yeah, all right, they're matching up nicely. What about the b? Yeah, it looks like, yep, that's it. That's the right answer. Okay, so what we've just shown is that this is true. And let's see, can we clean that up a little bit? I think that's about as good as it's going to get. Yeah, so any integral of this form is equal to this. And I will be using this formula in upcoming videos, so stay tuned. Hope you enjoyed that, and we'll see you next time.